I'm sure that this has been a long and a grueling week for all of you. And today, don't take any notes, and we're not going to use the lecture notes. Just sit back, and I wanted to perhaps tell you a couple of stories about the research. Those are research topics. And I'm going to be somewhat opinionated. And if you have any questions, comments, stop me. And one of the things you have to understand is you don't have to agree with me. Okay? And that's what's fun with research. We don't have to agree with each other. Let me just spend the first half of this morning talking about what I think, how do we get to a predictive combustion chemistry model. Okay. So I'll skip through that. Okay. So there are two problems that I want to talk about. One is how do you apply exponential quantum chemistry calculation and reaction rate theory to determine reaction rate constants. Okay, I'll use one example, CO plus HO2. Why we need to do that, and how did we do the calculation, and what were the answer we were getting, and how does it help us to understand things we don't understand. The second part is something that my previous student, David Shin, developed. That's model uncertainty. Recall that early during the week, we're talking about how do we handle with all the uncertainties. Okay. CO plus OH. Now, one of the issue with this reaction is this. This reaction is otherwise not that important. Okay. It's a very slow reaction. And if you look at its rate constant, if you recall, the collision limit is 10 to the 14. Roughly. And the actual rate constant at around 2,000 Kelvin, this is at 1,000 K over T, so 0.5 is 2,000 Kelvin, is around 10 to the 11. But at 2,000 Kelvin, you won't have that much HO2. So for this reaction to be important, most likely you're looking at a temperature range around 12 to 1,400 Kelvin. Okay, so it's right around here. But so the large activation energy phenomena causes this rate constant to be very small, around 10 to the 8. That's a rather small rate constant. Now this reaction does become important at a very high pressure. It provides a second pathway for CO plus for CO conversion to CO2. And I'm not sure if you can see it clearly. It's all too light. There's some symbols here. Did you see that? And some lines. So these are 3 plots made by my friend Jackie Song at UConn. Some years ago, he was doing this rapid compression experiment. And this is for a mixture of CO and hydrogen. And RCO is the ratio of CO to sum of CO plus H2. So this is almost close to pure CO. This is 0. What he found was that for the pure hydrogen, the model works just fine. But when it get to higher and higher concentration with CO, model falls apart. The question is why? Okay. Then at a time when he did the modeling study, he took this cluster of data, basically, took Fred Dreyer's, the compilation or recommendation from Fred Dreyer's group, which is more or less based on those set of experimental data, and that's this blue line. So if the model is that fast, okay, that means this rate constant, we did a sensitivity analysis, they found that it is this rate constant that's responsible for it. So so your next question is, how much you have to reduce this rate constant in order to reproduce the experimental data? Well, the answer is about a factor of 3. Yes, please.
Do you think turn off the front light?
Oh, yes. Good idea. Better? Don't That's better. Thank you. And if you have to have a rate constant factor of 3 smaller, then you fall out of the cluster of data over here. All right? So we were puzzled, and we were puzzled for quite a bit of time. It turned out that at the end we decided that all of these measurements are in fact very uncertain, precisely because it is easy to measure a fast rate constant, but it's very difficult in this case for this time scale you need to get the measurement right. So we sought to throw ourselves at this problem by doing a very high-level quantum chemistry calculation. Okay. Now, this is something called a couple cluster calculation with single, double, triple excitation, a directed calculation. The computation is done by my student, then the student Xiaoqing Yu, and she extrapolated the calculation to the complete basis set. So this is basically, long story short, for those of you who haven't done quantum chemistry calculation, this is basically a method that can ensure about plus minus 1 kilocalorie per mole of accuracy, okay, for the energy barrier. And now, what she found was that there was a peculiar thing about this potential energy surface is that there is a cis and a trans parallel pathway. You have CO coming in to react with HCO. Oh. Oh, okay, here. That's right here. Split it into. This is the reactant, CO plus HO2. So don't worry about this part of potential energy surface. Those are too high, don't have to worry about it. Just focus on this part. You have CO. You then have HCO coming in. Okay? You can do it like that, or you can do it like that. There are two conformations. That follows two local minima. At some point, they could merge. But in this case, they don't merge for most of the part of this potential energy. So you follow this trans pathway, that is, the thing, I don't know how to describe. You do it things like that, CO, HO2, you do it like that. Okay. You're going to get a local minima in potential energy, okay, which then rearranges itself, gets the CO2 plus OH by essentially dissociating the O bond. Okay. You can follow the cis pathway, but if you follow the cis pathway, you don't find a localized minima. Rather, you just go through a transition state and going downhill through some sort of cis-trans rotation. You get more or less the same product. Now, because we were interested in this problem, we want to know the accuracy of the calculation needs to be quite high in order for us to make conclusions. So one way you do that in basic ab initio electronic theory calculation, you can never ensure the value you get at the end is correct. The only way you're going to get some confidence in what you calculated is to use many different methods. Moreover, you wanted to increase the complexity of your calculation. Just like when you do a flame calculation, you want to adapt the grid. You do not know whether at the end you get a correct answer, but you do know that when you increase the complexity of the theory, you are getting an asymptotic value. Okay. And this is one example of it. We did a calculation, or rather Xiaoqing did a calculation at several different levels of theory. This is the lowest level, called G3B3. This is the highest level, called FCC-CBS. And in between, she played with basis set size from PVTZ to something that is a complete basis set. And indeed, what she found was that you start from this level of theory, you see the energy barrier decreases about 1.5 kilocalorie mole. And looks like as if it's getting into some sort of asymptotic value, but it didn't. And what worried me at that time was this is 17.9, this is 17.3. How would I know if I have a high order or high level theory? I'm not going to get a value that's smaller. So for that reason, I went to talk to Steve Klippenstein at Argonne National Lab. I said, Steve, can you do this calculation too? And I want you to use a different method. Steve is very good at this CAS-PT2 method. And it's not an easy method to use. He came back with the value of a 17.01, 18.2, 18.4. Now with the level of a theory going in this direction, he saw an increase in energy barrier. Okay. So at the end, nonetheless, this whole thing is sort of converged to a value between 17 to 18. We're getting pretty comfortable because with 1 kilocalorie per mole of accuracy, we should be able to make a conclusion at around 1,000 Kelvin about an energy barrier. That's about the rate constant of this reaction. So at the end, we used those values for the calculation. We used those values for calculation. 17.9, that's that one. Okay. Now, there's a second part of the story. Potential energy does not give you rate constant. It just tells you when reactants, intermediates, or reactants collide with each other, intermediates are formed. How should they behave on a potential energy surface? We need to do the second part, that is determining the rate constant. Okay. Now, the theoretical treatment assumption that we made was we used the Monte Carlo solution for master equation for collision energy transfer. Unfortunately, I didn't have a chance to talk about this yesterday. I'll explain a little bit here. We're using the exponential down model for collision energy transfer, and this part we briefly touched on yesterday. That's the RRKM, micro canonical rate constants. Okay. We determine a micro canonical rate constant for each and every channel. Those are rate constants as a function of internal energy. We then integrate it with the distribution, according to the distribution of a combined Boltzmann distribution for CO and HO2. And for this particular species, for excited species, we treated this by Monte Carlo approach because to solve for collisional energy transfer, yes, in case some of this adduct that's in the middle, that's the complex got stuck, we want to calculate it. Okay? And that's the Monte Carlo method that we treated this energy going up and down. And the rest, this barrier, that barrier, and that barrier, we calculated the microcanonical rate constant and again integrated everything. Now, one of the issues that we felt that we needed to deal with this problem was that this is in fact when you put CO and HO2 together, all of them are sort of a sigma-sigma bond. So it's a very flappy molecule that constantly rotate internally. Okay. Our early test shows that you're going to have to worry about those internal rotation and treat them very accurately. Very accurately to the point that not only the moment of inertia needs to be computed at a very high level, but also you have to worry about hindrance. This is not a free rotor inside. They sort of go through itself a potential energy surface. So we had to develop this, and in addition to it, this rotation energy, potential energy is not symmetric about the rotation axis. So we have to develop 1D hindered internal rotation approach using inverse Laplace transform, getting a partition function. So this I won't get into it, it's too involved. Now, the master equation code, early on we wrote this code. It was tested against the CO plus OH reactions. That's a different reaction. What we know is that for this reaction, we have plenty of experimental data. It allows us to check the validity of this code for measurements, against the measurement at temperature as low as 98 Kelvin. Now that's very difficult to do calculation at about 100 Kelvin. If you have a very small uncertainty in the activation energy, you're going to get very bad rate constant. That's number one. Number two, CO plus OH, if you recall, is a chemically activated reaction. We talked about this yesterday. Okay? Therefore, its rate constant is inherently pressure dependent with two possible channels. One is OH added to CO, forming this HOCO radical, HOCO. Okay. The second is that it will form this HOCO radical, then the HOCO radical dissociate into CO2 plus H before it thermolyzes. So if you measure the total rate constant of CO plus OH as a function of a pressure, you're going to see that at a very low pressure, it's a constant. At a very high pressure, it's also constant. In between, you have this transition from the low pressure to the high pressure. If the interpretation there is quite, the reason why how this happens is quite simple. The lower part has to do with the product, CO2 plus H. Pressure is so low, you form this HOCO complex. It has no opportunity to be stabilized. It must go out. Go out, one of the way out is CO2 plus H. However, if you increase the pressure, then stabilization becomes important. So it's the sum of these two rate constants that we're measuring here. And the symbols are experimental data. Lines are the Monte Carlo simulation. Okay. And that you can do this across a very wide range of pressure and temperature. And this is the typical Arrhenius plot. It's rather complex, so let me explain. The rate constant plot is a function of the temperature. And down below are measurements at a very, very low pressure, about 1 torr. And this is the measurement, not necessarily at the low pressure, but at a very high temperature. So this low pressure side of the curve represent rate constant for CO plus OH producing CO2 plus H. When you increase the pressure because of a HOCO formation, you're going to have those curves represent the production rate of HOCO. And you go to the very high pressure, 650 bar, then almost everything goes to HOCO. The symbols are experimental data. The lines are Monte Carlo simulation results. And as you can see, we can get prediction over very, very wide range of temperature. This is about 1,100 Kelvin, and this is about 2,500 Kelvin. Okay. This type of validation for the codes you use is important. It's important because it tells you that when you get a calculation, for example, I will show you the CO plus HO2, you have the confidence to make that conclusion that you want to make. So those intermediate steps are important. So back to CO plus HO2. And guess what? Indeed, after we did this rate constant calculation, we got this green line. Okay? Which is a factor of 2 to 3 lower than the early compilation results, and substantially smaller than experimental value. All right? We thought that, well, this is not good enough. Let me look into how uncertain my calculation is. How uncertain the calculation is may be computed by considering the uncertainty in the energy barrier, uncertainty in my treatment of hindered rotor, and uncertainty in moment of inertia, and everything you can think of. You estimate uncertainty of each parameter, and you redo the calculation for worst case scenario. Pushing the rate constant up, pushing the rate constant down. And what we realized is that the uncertainty that we definitely can determine still lies outside of experimental value. Now watch out. The point that I want to make here is that when you look at experiments, even though you have collaborating experiments here, different symbols represent different measurements. They are not always right. Okay, they're not always right. It is, so on the other hand, if you really, really want to get a calculation down with confidence, you have to go that far. Okay, you need to calibrate your code. You need to perhaps go to very high level of quantum chemistry code to get potential energy and the molecular parameters that you are comfortable with. And with that, you can make a conclusion. And then indeed, once we plug in the calculated theoretical CO plus HO2, we get a solid dark curve. And it agrees quite well with experimental ignition delay measured in Jaggie's rapid compression machine. Okay. Now, one of the things that I wanted to perhaps have a few minute discussion is about quantum chemistry calculation. Okay. The tool is so readily available to us. It is also very powerful. But that's provided you know how to use it. There's nothing that we use is a black box. Okay? And while I encourage you to fiddle and to play with those quantum chemistry code, and if you do, you wanted to do this a little bit carefully. And one thing first, if you're a mechanical engineer, it'll be fun to go take a quantum chemistry class from your chemistry department. Okay. One thing I can tell you is you won't lose. Your math is much better than the class average. But you might be able to learn a lot from what this code gave you and what are the results, how can you interpret the results. Okay. Any questions here? Yeah, go ahead.
Like my usual impression is that when you do the calculations, you tune the parameters such that it matches the experimental data. But in this case, I guess it's kind of the opposite, that the experiment doesn't have enough accuracy to predict the rate constant. So like, what do you think is the problem that not getting high accuracy in order to get the rate constant?
Yeah, that's a good question. That is all determined by how expensive and how involved in a calculation is going to be. And if you use couple cluster type of method or CASPT2 method, those methods we used, they are quite reliable. The part you may miss is a pathway that you did not catch. Other than that, if you have all the pathways for simple reactions, you're probably not going to miss a pathway. So for simple reactions like what we have, 4 heavy atoms, 1 light atom, you can use this type of high-level theory to do predictive kinetics. Okay. Now, when you get to 7, 8 heavy atoms, it becomes a problem because these methods are very expensive. You may have to rely on lower-level methods, but in that condition, you're going to have some experiment, as you pointed out, to calibrate your potential energy surface. Okay, that's also possible. In that condition, you are using the method. If you know your experimental measurements are accurate, you use the same thing we're talking about, except for with somewhat a lower level of quantum chemistry theory to do extrapolation. And that's variable too, because you can now do measurements over a very narrow range of temperature and pressure. You sort of anchor your molecular parameter against your measurement and then extrapolate. Okay, that's also very valuable. So both are possible now. It depends on what you would like to do. Okay. A lot of time, in the case of a second case scenario, you are doing extrapolation. And when I read papers in that subject topical area, what I wish people do is they actually tell us that my goal is to extrapolate the experimental measurement, rather than stating that we are doing ab initio calculations. No. Okay? There's nothing wrong by doing extrapolation. And if you have some experimental data, if you know it's accurate, use as much as you need to use it, because that gives you comfort. And at the end, what you are trying to get are accurate rate expressions that you can plug into a reaction model. Okay. So, you have a question, yeah?
Yeah, so from the quantum calculations, are you able to assess the, and I may be jumping the gun here, but assess the error associated with your prediction? So, you know, when I look at those two curves, and I look at the data between, and then I see, especially on the bottom one, you know, you're less than 5 milliseconds. I wonder if there is a significant difference between the two rate coefficients and the experimental data, just given that, you know, you're at such a small time interval. So I'm wondering, is there a way to assess the error with the...
Of the rate constant measurement.
Yeah, of the measurement, but also the prediction.
The rate constant, yeah. If you mean by rate constant, this I'll talk about later, the remaining uncertainty. Yeah, okay. And the uncertainty is here is represented by the two dotted line. Okay, so we know that uncertainty, and we can do calculation up and down. All right, going into here, and then we could do it, but it doesn't help us in resolving the fact that when you go at a low pressure 50 bar, we end up predicting here, we're over predicting there. But typically when you do a measurement, when you do a comparison between model, reaction model prediction, and RCM, don't try too hard. RCM does have the problem of internal fluid mechanics. Here you assume the calculation is homogeneous. RCM do have problem with stratification, flow stratification, do have a little bit of problem with heat loss. Okay, and when you observe ignition, you sometimes do not know whether this is a hot spot ignition or the whole volume ignition. Okay, there are many, many problems that you're going to have to worry about. So if you get this level of agreement, first of all, qualitatively things agree with each other pretty well. Quantitatively, well, you're 50% apart. That's good enough to me, in my mind. Okay. Now, one of the things, again, as you pointed out, you need to know, for those of you who do modeling and modeling only, I always suggest that you get yourself any opportunity to stay several days with experimentalists. Okay. Now, I was a theoretician. I took experiment data religiously. If I miss something like 10%, I got upset when I was a theoretician. Then I started getting myself to do experiments. And then I realized experiments are often very difficult. Okay? You get an appreciation. You get an appreciation for how hard experiment is, but it gives you gain a lot of respect for the experimentalists, but at the same time, the data you get, you take it not as a black and a white. It's a shades of a gray. Conversely, if you're an experimentalist, sit down one day with a modeler, ask the modeler that how accurate you want my experiment to be. And it's accurate enough to the point that I'll give you some information about what you wish to learn. Okay. So this type of experimental modeling interaction is how we can move the science forward. You cannot advance the science purely on the basis of a theory and a computation, and you cannot do this purely on the basis of experiment. The interaction is critical. Okay. I would have never thought I would ever deal with this reaction because I never thought it was important until this showed up. And when this showed up, I chased the Jackie. I said, Jackie, are you sure? He said, yeah, I'm sure. And that was responsible for us to go do this type of calculation. Okay. Let me get into the second part. Okay. Kinetic model uncertainty prediction and minimization. Let me talk a little bit about why we want to do that. All right. For those of you who have used the reaction models, and have developed reaction models or will be using reaction mechanism in your work, there's one issue you must be something that must worry you. If you look at the reaction mechanism, you have about a few thousand reactions, a few hundred to a few thousand reactions, right? And each reaction has a forward rate parameter and has its thermochemical properties associated with it. And if you look at the problem of flame, you have to worry about the transport properties. Okay. Now, taking this problem as a whole, there are several rate parameters that have been very well defined. H plus O2, CO plus OH, the CO plus HO2, and perhaps about a few tens of a dozen reactions, rate parameter. The rest, in fact, we don't know their values. So typically, the way how we do that, our Professor Green's automatic mechanism generation code, is to ask the question, are there any similarity among rate constant? Okay. Do we know empirical rules so that we can correct? If we know one reaction, we ask what does a reaction, what other reactions that are similar to this reaction? And can we do correction on the rate constant that we know and getting an estimate for those other reactions? Long story short, a reaction mechanism would have typically today, you're going to find about 80 to 95% of rate constant that are guessed. What saved us in this whole thing is if you want to do high temperature reaction kinetics, what has saved us in this whole thing is that typically for what you want to predict, those are ignition delay, laminar flame speed, flame extinction, they're usually sensitive to only a dozen reactions. A dozen. So if you get this dozen rate parameters right, you'll get a reasonably good prediction. Okay. But the problem is that you can never prove that if other rate constants are off or are off by 6 orders of magnitude, you would not know whether those rates would affect your prediction. Now, that's one issue. I stated this very earlier during the class, that if you treat each and every rate parameter, those unknown rate parameter, as an undetermined parameter, you would think that if I have 5,000 such parameters, I should have to do 5,000 experiments. You can inverse the problem, you get out the rate parameter. That's not that simple. All the rate parameters would follow Arrhenius kinetics, and you have to do 5,000 independent experiments. That's difficult to do. You measure flame speed at equivalence ratio 1.0, then you measure flame speed at equivalence ratio 1.3. These two experiments are not decoupled from each other. They're interdependent. Okay. So the basic mathematical question here is this, that you're going to forever deal with a problem that's mathematically underdefined. You can never do enough experiment, all right, to inverse the problem and get all the rate parameters that you need to know. That's number one. Number two, you also put down the question, can I just do reaction rate theory calculation for all of them? Yes. Taking 5,000 reactions, do ab initio calculation for each and every one of them, and getting the accuracy you need is a rather difficult thing to do. I'll tell you why. Today, the people who know how to do this calculation, there are probably 24 of them in the world. Each of them can do about 3-4 reactions. So every year we get about 30-40 rates calculated. And you have 5,000, how long do it take for you to calculate all of them? Not in your lifetime. So something has to be done here. Something has to be done here to address this issue. And that's the uncertainty. Let me just jump through that. When you develop a reaction mechanism, first of all, it's a model. You have to ask the question, what do you want this model to predict? Okay. So this is the laundry list we are looking at. typically you want this model to predict ignition. In most of the cases, we deal with homogeneous ignition, that is, ignition behind a refracted shock wave, or ignition in a rapid compression machine. Okay. Diffusive ignition refers to experiments in which you have a flow of a hot oxidizer impinged against a cold field. And if you increase the temperature of the hot oxidizer, eventually you're going to see ignition of the system. We want to predict the steady burning, that's a laminar burning velocity, and that can also be assessed by flow reactor, turbulent flow reactor. You stretch the reaction time scale, getting temporal and time resolution. That's steady burning phenomenon. Flame extinction, there are multiple ways of doing it experimentally. And you wanted to worry about a premixed versus non-premixed. And typically, we don't cover the entire range of performance requirement. Typically, when you write a paper working on a particular reaction model, you focus on one particular property. And you need to worry about a pressure concentration variation, and you worry about a global response versus detailed flame structure. Today, much of the work is still on detailed flame structure, getting major minor species concentration measured and compared to model prediction. Okay. So let me sneak in a little more on this. That is the question of how do you deal with large, practical, real fuels. Those are jet fuel, those are gasoline fuel, those are diesel. Okay. The way we deal with that, it was a hypothesis several years ago, and as a matter of fact, almost a decade ago, that those real fuel mixture are typically composed of several thousand compounds. So to write down the reaction kinetics for all of these components is not a scientifically tractable problem. Rather, what you want to do is to find the representative compounds, and hopefully about 4 or 5 of them need hydrocarbon, to mix them up and mimic the behavior of the real practical field. And you can define a matrix for which you want to measure, for which you want to match, and at the first physical level, you want to match the boiling points, for example. You want to match the distillation curve, and so on. At a chemical level, of course, you want to match the ignition, heat release, and so on. All right. So for us, there was an effort several years ago developing this surrogate strategy for jet fuels. Okay. Princeton was a major part of this effort, and we have our effort centered on the west coast. This neat hydrocarbon that represent components of a jet fuel are endodecane, butyl-cyclohexane, methyl 2,7-dimethyl-octane, and propylbenzene, and some tetraene or alpha-methylnaphthalene. So the strategy is to develop coupled reaction model for each and every one of these compounds. Okay, so we did one after another. And the way how we do that is to recognize that when you oxidize a fuel in a combustor, it does not matter whether you have aliphatics or aromatic hydrocarbon. You all end to have product that's carbon dioxide and water with incomplete combustion product, hydrogen, CO, acetylene, and soot. Despite that different initial fuel structure, the oxidation process do follow similar pathways, in particular at the small hydrocarbon level. So this is the foundation. In other words, does not matter whether you burn aromatics or aliphatics. They typically always crack, thermally dissociate, or undergo initial oxidation to form C2 to C4 hydrocarbons. Remember the beta-addition rule? If you start from alkene, whether it's a straight chain or branched, or cyclo, you take one hydrogen away, the whole molecule just falls apart by beta scission. And this beta scission is going to produce C2 to C4 hydrocarbon, and also with C1. So those are the foundation. Those are field specific. So we treat these two blocks somewhat separately. And the foundation has been developed for years. Okay, there are quite many reaction model for foundation field available. And one of us was developed by USC, and it took me about 15 years to get to where it was by 2007. And then we are going to trash it now and build a new one. I'll come back to this issue a little later. So one of the things we want to do in that whole process is no tuning, zero tuning. The philosophy is this. One of the things that bothered me was that when I see agreement between model prediction and experiment, actually doesn't teach me anything. It is when I see disagreement, then it starts to teach me something. Now the paradox, the problem early days I encountered was that if I write a paper, describe a reaction model I developed, and if I show line that doesn't go through the data point, reviewers will kill me. This model is no good. Don't publish. Paper get rejected. Okay? And when I tune the parameter, that's easy. Do you remember? I have a few thousand free parameters. I can always get every bloody line go over the experimental data points. Reviewer said, okay, that's a good model, publish it. But that is exactly the wrong way to go about it. I don't know if you've heard about this. One early days when I attended a combustion symposium, who is that? Klaus Hohmann, then a brilliant German physical chemist. And after one talk, I don't remember which talk it was, and their talk was about fiddling couple parameters. So he stood up and said that, you all know the story, right? If you give me 4 free parameters, I'll make an elephant for you. You give me a 5th parameter, I'll make this elephant walk. And that's true. Parameter tuning is never, especially for an ill-defined mathematical problem, is never the way to go about it. Okay. So the point I want to make here is that next time when you see disagreement, and if you see fundamentally this problem cannot be resolved, don't tune the parameter. Be proud. And discuss it, write your paper. Maybe you'll get a good experimentalist interested in this problem and redo the measurement. What the correct answer is, correct approach to this problem is to say, well, they don't agree. I know what causes it. And if you can do this measurement under that condition, give me an answer, X, Y, and Z, I will be able to fix this problem. Okay, and indeed, we have a collaboration going on here that involve, maybe I want to show this. It's a huge collaboration that involves USC, Stanford, Princeton, Drexel, NIST, Imperial College, and University of Michigan. The rule we made early on is very simple. A, we don't publish reaction mechanism. B, we tell people this mechanism, this model is never going to be perfect. C, whenever there's a problem, experimentalists are going to have to find an answer for us. So as a model developer, my job was to identify problem. Okay. And that turns out to be a very useful approach. In some cases, we were very successful. In other cases, we were not. And this is one of the successful example. That is, the solid lines here are multi-species time history measurement by Stanford group, Ron Hansen. And the dashed line are model prediction. This is all without tuning, and you can get that level of accuracy. Couple issues. Here, Stanford group was able to take N-heptene at 300 ppm, equivalence ratio of unity, shock heater, then follow the intermediates and the products. Okay. What you find is by first 10 microsecond, the fuel is gone. Dissociated to ethylene. Why does it dissociate to ethylene? Beta-scission. Now you see how fast the beta-scission is. Okay. You have 1 to 10 microsecond here. I cut it off in a plot because I wasn't sure whether we get a vibration relaxation problem in shock wave, but that's a different story. All what I know is beyond 10 microsecond, the experiment data are very reliable. And what we do know is the field goes almost all to ethylene and some to methane and C3 species. Dominantly goes to ethylene. Then the problem becomes waiting for ethylene to ignite, and ethylene and other small components. So this illustrated my point that going earlier, if you wanted to have a reaction model for oxidation of large aliphatics, what really matters is perhaps this chunk. The dissociation of the aliphatics to the small hydrocarbon is rather fast. Aromatics is a different story, and aliphatics at least, branched, straight, cyclo, they're very fast in giving you small hydrocarbon. So typically for a high temperature oxidation problem, you're basically looking at oxidation of small hydrocarbon. Okay. You have ethylene formed, you have a little bit of initial production of hydroxyl radical, but then the system gets quiet. It's quietly building radical pool. As it builds radical pool, water concentration must increase, right? Radical produced. It's going to go, some of that goes to attack molecular oxygen, while others goes attack the ethylene and other small molecular fragments. So water forms early. All right. But you start to build a radical pool until about 100 microseconds, the OH concentration take a flight, take a rapid rise, and this is accompanied by the rapid production of CO2. Now this chart is a representative of the structure, the time structure of fuel oxidation processes. Okay. Going back to what I said, the solid lines are experimental data, the dashed line is a model prediction, so we were feeling pretty good. This approach is working. But then we ran into one next problem. I'll illustrate this here. And this is what we all do for years. Now, typically when you develop a reaction model, you follow these sequential steps. And if you develop a reaction model for your PhD thesis, you probably go through 1 or 2 of this cycle. Okay. Now, first is a critical review of literature kinetic data. All right. Today, the problem is too big. It's not possible for any of individual person to do evaluation for every rate constant that goes into your mechanism. Typically, you're going to have to take some models off the shelf and expand on it. How many of you have developed a reaction mechanism from scratch? Scratch meaning an empty piece of paper. No. And I only know there's one person in the world who did it. Okay. It's a tedious task. It's a tedious task. And one of the issues here is that most of you, when you develop a reaction mechanism, you use someone's foundation mechanism as your basis and you build on top of it. All right. And I was fortunate to belong to that generation of people who actually started building things from scratch. I didn't know not do the whole thing, but I did a big part. A big part of a small hydrocarbon chemistry. And take years to do it and get it right, and take years to revise it. It's annoying. The time you have a reaction model, somebody did a measurement and said, your rate constant is off by a factor of 3, and the whole foundation is shaking. What do you do now? Do I have to go back because the model has been validated against the hydrogen, CO, methane, ethylene, And it's a lot of work. For each field, typically you have to validate this reaction model against something like 50 sets of data. That computation itself is time consuming. Okay? So you just go round and round and round. For years we've been doing that. But then we are doing round and roundabout. Everybody else is doing round and roundabout too. That is, if you take idealized model approach, you do a literature kinetic data review, you compile your model, reaction model, and in many cases, the model is not going to predict. So you do some tuning. And that tuning is left, you call validation. And validation and tuning are basically the same thing. Once you tune it, you invalidate the model. But let me just, for the time being, assuming this is still valid approach. And once you validate it, means that you have some curves going through experimental data. You then go publish it. Okay. And a single approach exists today. Go open the Combustion and Flame journal. You will see many papers are doing exactly that. The problem is when you have many papers doing that, you have parallel effort. They don't talk to each other. Suppose you are an engineer working for an auto company. What do you choose? And I can tell you the last 24 months, we saw 24 butanol combustion models. How many of you are involved in that 24 butanol models? I didn't mean to make you feel bad.
I think we experimental.
I'm sorry?
Experimentally.
You do experimentally. Nobody else contributed to the butanol model? You did, yeah. Experimental. Now I feel if you did experiment, it's good. Data. Okay? And hopefully you want all this 24, it's not 24 group, it's about 1 dozen group. But then I have to ask you one thing. You know, if you ask me, I never want to publish 1 of 10, a dozen models, unless I know how to do better, okay, and how to resolve this problem. So this, what I call the divergent approach. Now, suppose you're going to use butanol as the fuel in the engine. What do you tell the engineer? Which model he or she should use? Now, all of us have our own prejudice. That is, if it's my model, it must be better than anyone else. But that's not scientific, you know. It's not opinion. It's not a fact. So what do we do? Yeah.
Compare them
I'm sorry?
and let them compete against each other.
You compare against each other. So that's what we do now also. If you open up a combustion of flame, you have experimental data, then typically you use 2 or 3 models and compare them. The trouble is, what happens if model A agrees with data set 1 better? Model B agrees with data set 7 better. Most of the time, you run into, that's what you see. You say this model works a little bit better for ignition. That model works a little bit better for flame propagation. And if you wanted an application that you need both, what do you do?
Combine.
I'm sorry? Take average. All right, I'll tell you my problem with IPCC global warming prediction at a quantitative level. If you notice, if you read IPCC report, the prediction for extendable global warming, all the models agree that there will be certain warming in the next 50 years to 100 years. What they disagree on is the amount. So when you make recommendation, what do? There are 26 models out there, global climate models. Indeed, it's based on average of the prediction by about this 2 dozen models. As you formulate an uncertainty on the basis of a scatter of the prediction. But a model is our way to understand the nature. Model, as a scientist, is our microscopic religion. How do you average the outcome of a model? You can't average two religions, right? And I say there's an uncertainty. That becomes a fundamental problem. Okay. What they do disagree is inside the model parameters and perhaps a couple of conservation equation terms. There are different models. All right? But at a model prediction level, it's too late to do that average. So the question that I have is, well, are these two reaction models fundamentally different? And a more logical way to do that is go into the reaction model, compare every rates, put them next to each other, okay? Add the rate constant up divided by 2. You start to average on the rate constant side. Then you get a single model. Well, not all reactions model have identical reactions. Some of them have more of this, some of them have more of that. And I would say not specifying a reaction basically is to say this reaction exists, but I'm assigning its rate constant to be equal to 0. 0 plus 1, you average it out is 0.5. And for many rate constants, it's not the same because it's Arrhenius behavior. And you average something of 1 and 0 gets you 0.5. It isn't bad. Your uncertainty is a factor of 2. Wouldn't it be better if we average on the rate constant?
Can I make a comment?
Yeah.
For a lot of calculations, experiments, there are different uncertainties, so you cannot average those of the calculation result experiment data. So you must identify which experiments is more reliable than the others, which theoretical calculations have better, expectation than the others, right?
Okay, what you are saying is not all experiments are created equal, and not every rate expressions were measured, or determined, or evaluated equally.
Yeah.
All right. Those are problems. All right. And literally, I have to tell you, for years I was stuck with this problem. I did not know what to do. I knew I have something to contribute, but I do not want to contribute another Butono model so that I don't add much to this effort. Okay. So we had to spend the time to look at this issue and asking how can we deal with it and how do we do better? And there the problem is we have a proliferation of models. That's the phenomenon I call it. All right. Yeah, go ahead.
I guess what seems like where you're going, and my question overall too, is that why do we need a single model for a single set of chemistry? So if you want something that actually is predictive accurately, wouldn't you think, okay, well this one works really well for flame speed, so use it for flame speed calculations. This works great for volumetric. So I guess it's nice to have a single model, but why do you need to have a single model? Is there some fundamental reason why we're pushing that way?
It's prediction.
Yeah.
There is a you want.
Like you need to know the flame speed or the ignition.
Well, but you usually need to know that to validate the model, right?
But the science is there.
No, it's
There's
for
only one
prediction.
correct science.
No, but see, I think that's tough. Like you're assuming that there is you will eventually end up with a model that is 100% right. I guess my contention is I don't know that you ever would.
Let me give you my 2 cents. It's a good point. And let me give you my 2 cents. If the model eventually, the purpose of what we do, aside from scientific understanding, the purpose is to combine this with a computational fluid dynamics code to simulate a gas turbine. And in this gas turbine combustion, you're going to see flame propagation. So you have to get flame speed right. You have to get heat release right. You see local extinction and reignition. So you have to get ignition right. You need to be able to predict the nitrogen oxides production. That's, after all, a large part of the reason why we use detailed reaction mechanism. And in gas turbine engine, it produces soot. Radiative heat loss becomes an issue. You have to account for it. So the problem is, the issue is, when we develop this reaction model, we have in mind that it must be able to predict everything. Okay. The fact that we validate this model against the laboratory experiment was just to say, to give us some idea and assurance that we're not too far off against reality. And for us, reality in the lab is a well-defined experiment. RCM, laminar flame speed, ignition, shock tube ignition, and so on. Even so, we cover only a very small thermodynamic condition space compared to gas turbine engines. So that's a practical consideration. Okay. A theoretical consideration has always been, we, the scientists and the human, always have this behavior. We want to unify things. Well, it's just like you have the relativity theory of the quantum mechanics 100 years ago. They don't talk to each other. Got Einstein really worried. Spent the rest of his life trying to find a unified theory. Okay, and that effort is still ongoing. You always want to find a unified theory. And this is not to say that seeking unified theory is always the right approach. All right, but that's how always we approach things that way. Okay. And at the end, well, you go to turbulence simulation. You have the LES model, you have the DNS, you have all RAMs, K epsilon, and so on, so forth, right? And you have different LES models made, and the goal at the end is still is you have to unify, and find a way to unify. Any other comments about this issue? Yes, please.
When you were asking why models can't just match the experimental data, like why you have a model for flames and why not for flow rate? The way I see it, there's two different types of chemistry. Well, three. You've got low, intermediate, and high temperature. But if your high temperature model doesn't match all of the high temperature experimental data, then there's something wrong with the model in that if it matches the flames but it doesn't match shock tube data, then you're missing a few reactions because the flames will depend on small species, so your decomposition reactions don't matter too much, whereas the shock tube depends on more field-specific reactions. So if your shock tube isn't working too well, then I wouldn't think that you have the chemistry of the actual field reaction. So that's why I think it would be great to have one model that fits all high temperature, and then in the end, one model that fits the whole temperature range.
Yeah.
Plus, the whole point of developing any model is to predict. Otherwise, why do you need a model? To theoretically, computationally, whatever you want to do. So you have to have it so that it contains, if not everything, but to an extent something. Right?
So to predict. So let me follow up and give you my opinion of what prediction really means. Okay. I'll make this statement earlier. We talked about a few days ago. When you listen to weather forecast, that's a prediction. How do meteorologists make a prediction? By computer models. Okay. And typically every 6 hours, they took the measurement from various locations for which you cover, and then feed it back into the model. You predict the next 6 hours. And you also have a long-term prediction, but the more long-term you predict, the less certainty you have. So typically you listen to weather forecast, you say tomorrow is 40% chance of a shower. Now that is not to be misunderstood as an uncertainty statement. It just says that tomorrow we know there's a 40% chance for a shower, and most likely it will shower. That's a time statement. It says tomorrow at 9 p.m. there's a 40% chance for a shower. But then there's also second uncertainty of prediction. That is, you projecting out to the end of the week, and typically the statement becomes less than firm. You get to a cloudy versus a sunny day type of statement. Okay. For weather forecasting, the uncertainty is more important than the actual mean. we can all deal with our life, whether it's a rainy day or it's a sunny day, a cloudy day. We know how to deal with it. But it is the uncertainty we need to deal with. And that's more important. Okay? Now, simple things about today I have to make a decision based on what I predict, whether to bring an umbrella or not to bring an umbrella. Are there extreme conditions when you snow, when you have sleets? That becomes even a big problem. All right. So meteorologists know that the prediction, all the prediction is all about uncertainty. All right. In combustion, we're not there yet. But if you ask an engineer what he or she needs in a design process, a nominal value predicted is useful. For example, how long is your flame going to be? How long a flame is going to be determines roughly how big your combustor is. So you predict this to be 50 centimeter. Okay? And you present these results to your manager. Your manager said, oh, that's very nice. You have a prediction. But today, if I ask, I'm simplifying this whole thing. Now let's design this engine at a 50 centimeter. Don't you have to go home and feel very insecure? What if my prediction is off by 20%? If the combustor is not big enough, I'm going to lose 30–40% of her heat production. And that's big. Alrighty? And then the other side, of course, is that I build a combustor. I remember this story that Kathleen Foutage, a good friend of mine from Princeton time, and he is at UTRC, a manager at UTRC. UTRC, United Technology Research Center, is a subsidiary of UTC. UTC owns the company called Carrier. Carrier makes water heater. So one of the combustion problem they had was this little heater, water heater, the natural gas combustor. He had to deal with an acoustic problem. That is, well, a Carrier has this thing and it makes it heats the water fine, but it whistles. So he had to kill this acoustics. With the condition this burner has to be produced for less than $1. That became a challenge. So making predictions impact how much it's going to cost for you to produce something. All right. Now, in any companies, when you start to talk about the money, things become interesting. But then again, when you make a prediction, you have to worry about uncertainty. Okay, you can't go justify say, well, this engine is going to make you money. In your own mind, even if you don't tell your manager, you're going to have to be able to assess in your own mind, am I making fool of myself at the minimum level? Okay. So let's talk about this uncertainty and how I think we should move forward with this. And let's come back to what we talked about earlier, about the many different models. The many different models don't fundamentally agree in reaction pathways or not even rate constant. It's just a statistical sample of the uncertainty. I choose a rate constant, you choose a rate constant, you choose the value of a 2, I choose the value of 2.01. You ask me why. Just because that day I had too much coffee, or not having enough coffee. Those are random events, many of it, in many cases, led to different reaction mechanisms. Okay. Sounds like an insult to people who do that, but the reality is that we all agree that we usually don't goof for important reactions. Okay. For example, H plus O2 producing OH plus O, that's a chain branching reaction. And if you go back to look at Bauch's 2005 compilation, he threw all the reliable measurements on a single Arrhenius plot. And you see the scatter in the data. Okay? And it's 50% up and down. So if you take the mean you're going to get a 25% up, about 25% down. That's your uncertainty. All right. You're asking the next question. If I were just to account for this reaction, how much impact do I have on what I wish to predict? Let me take a benign case. Ethylene air flame speed is F should be phi, an equivalence ratio of 1 pressure equal to 1 atmosphere. Okay. And I can calculate a sensitivity coefficient. That's D log SU, D log K. Where SU is the laminar flame speed, K is this rate constant. I get a value of 0.24. Okay. From this 0.24 value, I can take this 25%. After all, once I know the uncertainty, I can perturb the K, right? To get a change in laminar flame speed. And what I calculated over here is, with this uncertainty allowed, I'm going to get a plus minus 5% uncertainty on the flame speed prediction. That's 4 centimeters per second. The laminar flame speed of ethylene is about 80 centimeters per second. So 4 centimeters per second, that's rather large. Okay, but that's only one reaction. And I have another few hundred. The question is, what do you do? Now, the key question is, how do we propagate this kinetic uncertainty from elementary level and to prediction in combustion? And why I think this prediction is important, this illustrated the fact that I discussed earlier. All right. This are, this is not supposed to show up yet. Yeah, I get rid of it. Now, most of the data available for hydrogen oxidation and a hydrogen flame were at the low pressure, 1 atmospheric pressure. After all, it's easy to do measurement at 1 atm. Okay. Somewhat recently, the group here, Yu Guangju and Fred Dry, made measurements for high pressure mass burning rate of hydrogen oxygen helium mixture. And those are those points. Okay. And somewhat earlier, there was a measurement by Professor Law here that is those open symbols. Most of the models were validated against low pressure data. And I only accounted for models published after 2000. There were about 10 of them. Remember, hydrogen oxidation is the foundation. If you start to bifurcate at a hydrogen level, you're going to end up with tremendously large array of a reaction model. They don't talk to each other. So Yu Guang, Professor Zhu was very good at saying, well, we're going to have to do this at a hydrogen level. And that's what he found. Experimental data, then you have several models. And they spread rather wide, from the lowest, GRMAC 3.0, to the highest, Professor Karnoff's model. Okay. So if we do the model comparison, when we write a paper, we would say, here it should go. Those on the outlier are very bad. Those on the edge are bad. But then that set of happen that go through the data points, you say it's good. But I state you aren't very lucky. Look, we've known a lot about this pressure condition. We know very little high pressure rate constant. If you hit it, that might be fortuitous. Okay. Well, it turns out this wasn't fortuitous. And I don't want to explain too much here, except to say this model was mine. And I fudged it. From early day, before I had this data, there's a fudge that I did. But that's a good fudge. So let me tell you what do I mean by good fudge. It's not about rate parameter tuning. It's about how do you deal with this problem as an inverse problem. Okay. So the phenomena that we see here, I think ought to get you very worried. The state of combustion chemistry at the level of a hydrogen oxidation is that uncertain. you build things on top of it. How would you know your foundation is accurate? For without a good foundation, everything on top of it is going to be shaky. Okay. My interpretation at a very fundamental level is this. You have rate parameter uncertainty. I showed you the uncertainty in H plus O2 chain branching. Okay? That's the most important reaction, but there are many others. And you have data uncertainty. That is, when you measure flame speed, you have uncertainty associated with that. And in between, if you collect reactions into a reaction mechanism, or model, you also collect the uncertainty of the rate parameter into the model. And they talk to each other through some sort of physical problem description. For example, the governing equation of premix code, premix flame. Okay? Mathematically, you can propagate one into another. So if you define a reaction model at this point, remember, we all agree on the pathways. We just sometimes disagree on individual rate constant. If I view this disagreement as a statistical sample for each uncertainty of each and every parameter, then what I'm providing, those models I presented here, each one of them is a random sample of the statistical uncertainty in the rate parameter. Do you agree? Okay. Collectively, it forms a model. A model represents a point in this uncertainty space. So when you filter this out through the physical problem, you get a prediction. You're here. The next model is going to be here. It's going to predict there. So the phenomena we are seeing is exactly we're doing that. Now, one thing I have to tell you is that once I understood, it took me many years to understand why does this happen. And once I understood this phenomenon, I said, I'm not going to generate a random point over here. In any reaction model I develop, it's going to be a random point. If it's not going to be a random point, you're going to have to account for the whole uncertainty. But if you can account for the whole uncertainty, how do you propagate them into what you wish to predict? And more importantly, back. If this is my model uncertainty, this is the experimental uncertainty. For example, laminar flame speed, you can measure it to an accuracy of plus minus 1 centimeter per second. Whereas my model uncertainty is plus minus 4 centimeters per second. And the experimental data must contain useful information. You want to propagate this backwards to define a coupled uncertainty space so that that's the way how you can approach the accuracy. Yes?
Isn't there any sort of distribution of the rate parameters within the parameter space? You're assuming there's an equally uniform distribution.
Oh,
Shouldn't
yeah.
there be some sort of
Right now, we have two model assumptions for the uncertainty. One is square distribution. In other words, if you're going back to this, we assume that my uncertainty is defined by this band. But inside of this band, every point is equally probable. So that's a square uncertainty, square distribution. We also make assumption that this is a Gaussian distribution. Okay, most probable you take the mean, but the edge represents the two standard deviation. You can make both assumptions, and as a matter of fact, you can throw any uncertainty PDF into description of this reaction mechanism, rate parameter. So then you ask me next question, well, that itself is a model. How do you know you're doing the right thing? Number one. Number two, how do you actually accurately assess this uncertainty model? That second question I know the answer. The first one I do not know. The second answer to second question is that it depends on rates. Depends on reactions. For this reaction, the more valid model is probably a Gaussian distribution because you have enough data. For some other reaction where you only have done measurements for 2 or 3 times, you don't have enough data, then you're going to have to assume the square distribution. Okay. Interesting enough, this was when David Shi, my ex-student, did this. That was my first question. I said, how do you know the distribution function? So what he found was that now what he does is he does both. After all, Gaussian is one limiting case, right? Square distribution is another. All what you want to make sure is the conclusion is not affected by your assumption for the rate parameter and uncertainty representation. Okay. So the method was called uncertainty minimization using polynomial chaos expansion. Its utility goes like that. As far as the laminar flame speed prediction, this doesn't have to be laminar flame speed, can be shock tube ignition delay, can be species concentration profile in a flow reactor in burner stabilized flame. The goal is to present your prediction in the form of a band rather than a line. A band that represents all kinetic uncertainty of your model. Therefore, each rate constant now in the model that we have has an uncertainty factor associated with it. And you include this uncertainty factor in your calculation. It's not that hard. I'll explain the math a little later. You're going to be able to develop this 2 standard deviation band for predicted laminar flame speed. And more importantly, you can also use experimental data available. Well, the model uncertainty here is larger than experimental uncertainty, so experiment is more accurate than the model. If so, you can inverse the problem and constrain the model, right? The uncertainty model. You cannot pin each and every rate parameter, but starting from, say, 2-parameter space, you can say only here can reproduce the experimental data plus its uncertainty. Okay, that was the goal. Yeah, go ahead.
When you reduce the uncertainty, then, so like this laminar flame speed is a bulk property or a bulk motion or activity. So how do you choose which rate coefficients then to change, right? Because at some point you're going to have to go back against the old data and say this is actually more accurate than we measured it before.
That's right. Typically, what we do is a uncertainty is a sensitivity calculation. Okay. You don't want to constrain every rate parameter, or you don't want to fiddle with every rate parameter. You know, if you look at what you predict as a function of all these rate parameters, you never ever wanted to do anything for the measurements you have, do anything on those rate parameters that impact your prediction. If you take a derivative of what you want to predict with respect to a particular rate constant, if it's 0, then the measurement gives you no information about this parameter itself. In other words, if you have done sensitivity analysis, you know the derivative is 0, sensitivity coefficient is 0. Okay. And you only do operation on those that has a finite derivative or sensitivity coefficient value. Okay. But that's essentially handled mathematically. All right. When you do minimization problem, you're going to have to inverse the Jacobian. Then when this thing blows up, you know something is wrong, you don't want to go there. It's a mathematical thing. Okay. So this is, after all, the goal, the utility. So how do we do that? Well, it's actually not that difficult. Let me do the bottom part first. Now, in the past, and when I was young, when I was trying to get my reaction mechanism and the model right, I wanted to do sensitivity analysis. And once I did a sensitivity analysis, when I do some tuning of rate parameter, it's very tedious. That is, you change one rate parameter, you send the code to run, and say, what's my laminar flame speed now when I change my rate constant by factor of 2? You have to remember, late 80s, early 90s, computers ain't that fast. When I calculate laminar flame speed for methane, I have to wait overnight. Okay? I have to wait overnight, and it's a very tedious thing because every day you are allowed to know only the outcome of changing one rate constant, what impact it is on your flame speed. So Michael Franklin and I came up with the solution mapping method to recognize that if you do not perturb your rate parameter too much, then for what do you want to predict, for example, the laminar speed, you can represent this by a Taylor expansion. Okay, where x here are basically rate parameters. We generalize it. It can be enthalpy of formation. It can be equilibrium constant. It can even be a transport coefficient. So x represents a model parameter. Okay, and you can express what you want to predict as a function of polynomial. So the first term here, this a, is basically the sensitivity coefficient, the linear sensitivity coefficient. That's the coupled sensitivity coefficient. Right? All right. Do you recognize when you do a sensitivity calculation, all what you're doing is you are doing this term? Okay? Quantitatively, as a matter of fact. It's not qualitative. Okay? And you can also determine the higher order terms by looking at if I increase the H plus O2 chain branching and H plus O2 termination in the same direction, how does my flame speed impacted? Okay? Or if I increase the chain branching rate, decreasing the chain termination rate at the same time, how is my prediction get impacted? So this is called a second order sensitivity coefficient. So solution mapping is nothing more but a quantitative sensitivity analysis. So once you have this sort of expression, you can plug in easily what you want to see into this polynomial expression, and you get prediction very fast. And typically for flame speed, ignition delay, or anything we encounter in combustion, with the exception of extinction limit, I can express what I want to predict with respect to the rate constant by a second order polynomial. Okay, but that's just cheap math. So now this is a parameter. Yeah, go ahead.
What is the alpha at the side?
Huh? Those? Okay, I'm talking about here first, and I'm going to go up there. Okay, I'm getting there. We probably should take a break, yeah? I'll finish this slide and we'll take a break. Okay. The X is rate parameter, thermochemical data, or anything that goes into the model. And now I want to represent uncertainty of this X. How do I do that? I go to Wiener's approach, that's called a stochastic spectral expansion. I express a parameter of its nominal value plus its fuzziness. And this fuzziness is represented again by lower order and a higher order term. If you throw away the higher order term, then alpha is a coefficient. This is essentially a random variable. This random variable is determined by and large by the distribution you assume for this rate constant. Okay? The simplest thing without thinking about anything else is you have a coefficient alpha. Its magnitude determines the uncertainty here. But this is a random variable. You can just do it in Monte Carlo approach, getting a scatter sort of thing for this xi. And if you get a scatter, you plug it into this equation, you get a band. That isn't hard, right? Are we okay with that? Okay. So the caveat in this whole thing is about developing this response surface. Okay. I sure hope I've been talking to reaction design for years. I said, you made all these codes. You have sensitivity analysis. You already have this term. Why don't you increase one more order that's get a coupled sensitivity coefficient? So then when people do flame speed calculation or sharp tube ignition calculation, what you should get out is this, rather than giving me that only. That's not difficult to do. Okay? And once you have that, this polynomial, the solution mapped, then if you have uncertainty, you can plug this linear algebra. This just becomes a simple linear algebra problem. All right. So the point I want to make is that getting this band isn't hard at all. You all have the capability to do it. A small extension of your capability. So today we do this simply by taking, for example, the flame code. David automated, you push a button, what you get out is this. Okay. And he's even automated that you push a button, it goes straight to a band. It can be done. Okay. You want that computer code, just talk to David Shing, he's at a NIST, and I'm sure he will be happy to give you the code. Okay. Now, we'll take a break right after that. The reason the utility of this simulation is also the other thing. If you, I'm not sure if you recognize now. If you do a nominal prediction, you compare to the experimental data. If you have a line that looks like that, your advisor or your manager or whoever is going to ask you, why doesn't it go through the data? When that happens, does that really mean your model is wrong? No. It's just because of uncertainty of the model is large. Okay? And you wouldn't have a problem seeing that, right? That is, this is to state if I have a model that gives this line, I'm within the margin of our knowledge, or uncertainty of knowledge. If I have the upper curve, that's also within the margin of knowledge of our knowledge, right? And that's a much better way to look at this problem. You no longer look at what is wrong, but you ask the question, what is inaccurate? And if it's inaccurate, how do we get this accuracy based on experimental measurement? So let's take a break. We'll come back, 20-minute break? Okay, 10:40 is when we're going to meet again.